Hello and welcome to this online video lecture over the advanced topic of Gibbs free energy, sometimes just referred to as free energy. Probably one of the most advanced concepts we're going to get into this year. Gibbs free energy is really not that bad. The math is actually quite simple once you understand what the heck you're doing. By the end of this video lesson, you should be able to calculate the change in Gibbs free energy for a chemical reaction, then use that information and some others to decide if the reaction is spontaneous or not, and whether or not the reaction is endothermic or exothermic. So let's get to this. Gibbs free energy. It's basically named after the scientist that came up with the idea or developed the idea. His last name was Gibbs. And the concept is it's called free energy because it's the energy inside something, whether it's a chemical or some kind of machine or something like that. But it's the energy inside of something that's available to do some kind of work. And that's why it's called free energy, because it's available, it's free to do some kind of work. And as with most things in the universe, when we're talking about Gibbs free energy, the universe tends to favor a decrease in this. So it wants that energy to be less ordered, less structured, more random, and less useful. So, processes in which the Gibbs free energy inside of matter goes down are favored and tend to be what we call in chemistry spontaneous. Now, we're going to get into the details of that a little bit later, but I do just want to really quickly mention, and you might want to come back to this if you start to get confused, that when we say the word spontaneous in chemistry, it doesn't quite mean exactly what the everyday usage of that word is. Basically, in chemistry, when we say something is spontaneous, that basically means that you can kind of think of it as it will happen. Once it gets started, it's going to go to completion without you having to do anything else to it. Spontaneous reactions sometimes require a little bit of energy input in the form of heat or electricity or something to get going, but once they do get going, they continue to go until they are done. Those are called spontaneous reactions. A non-spontaneous reaction, you have to constantly keep doing something to the matter in order to keep the reaction going, and as soon as you stop doing that to the matter, then the reaction would stop. So that would be a non-spontaneous reaction. Okay. So let's get into Gibbs free energy. I guess we'll just start right out with the formula. It's actually not that bad. There's only 4 terms to it. So we're going to use our deltas that we've been seeing so much here with thermochemistry. The change in free energy, Gibbs free energy, which we're going to represent with a capital G, is equal to the change in enthalpy, which we've done before. So heat of formation, basically, right? Can find us our change in enthalpy minus the temperature that the reaction is occurring at times the change in entropy. So let's just talk about this change in entropy term, because we've talked about what entropy is, but we've never really done any math with entropy. You'll notice that delta S looks a lot like delta H, and that's and also a lot like delta G, and that's because those are all changes. So let's think about how we calculated this change for the previous advanced quiz. You take the sum or the total of the final state, which would be the products, and you subtract the sum or the total of the initial state, which would be the reactants. And that's how you find the change in enthalpy. That's exactly how you find the change in entropy. You take the sum or the total of the entropy of the products, and you subtract the sum or the total of the entropy of the reactants. So I don't have a quiz and a lecture over that specifically because it's so similar to finding the change in enthalpy. You do it almost the exact same way. The units are a little bit different, but I will walk you through that in a problem here in just a few minutes. So that's your formula right there. You got to multiply the temperature of the reactions occurring at. Of course, it has to be in Kelvin, right? The temperature has to be in Kelvin. And you multiply that by the change in entropy, and then you take your change in enthalpy and you subtract the product of those two things from that, and that gives you the change in Gibbs free energy. And if the delta G is negative, then that is a spontaneous reaction, like I talked about earlier. And as you can probably guess, if delta G comes out to be positive, then that is not spontaneous. Ooh, my O got away from me there. All right. Okay. So that's kind of all the conceptual stuff. This is a pretty math-heavy lecture here. So let's just get right into an example, and I can show you what a problem will look like and how you work your way through it. Oh, one more thing, I almost forgot. In order to do all these problems, you're going to need a data table. And so what I've done is I've put a few in the course for you to pick from. The thing about these data tables is that they might not have every single compound, unfortunately, on them that you need. So you might want to print off like one or two of them, or print one and then have access to the online one. But let me show you right here. I'll pull it in real quick. So here's the course. You can see. Let me just make that smaller. And here's I'm about to put the lecture. But here's Advanced School 7.6, and you can see there's 3 table options here. There's an online one and there's 2 printable ones. The printable ones I've got living on my Google Drive. So this one, you'll see at the top, this one gives you heats of formation for different substances. It actually gives you delta G's for those substances from their elements. And then it gives you they call it absolute entropy, which is this column right here. That's what you need to calculate the change in entropy as well. So that's just an example. That's one of them. Let me see. The online one looks like this. It's very, very similar. And then there's one more printable one that you can use. But you are going to need one of those tables. I'll be hopping back and forth between them as I do this. So I'm just going to push that over to the side for now. Okay, so let's get into an example. I'm going to go ahead and write a problem out. I'm going to pause the video and then I'll come right back when it's done. So it'll pop right up on your screen. Okay, so basically when you have a problem like this to solve, you're going to get some kind of a chemical equation. What I've written here is the chemical equation for the dissolution or the dissolving of ammonium nitrate in water. So when you throw some ammonium nitrate in water, it dissolves and it breaks apart into the ammonium ion and the nitrate ion. Now there is one thing about this reaction that's a little bit sneaky. And I picked it on purpose so that in case if you ever encounter it, you'll know what to do. But I would like you to focus for a second on the water. And you'll notice that for some reason in this equation, water only appears on one side. And that should raise some red flags for you. You should know that in a chemical equation, you can't create or destroy matter, so you should have everything on both sides. So basically, what we would call water here is we would call it a spectator, and it's not directly participating in this reaction. You can kind of think of it like a catalyst, but that's going a little bit far for a solvent in a dissolution like this. But because it's not on both sides, you're basically going to ignore it for this entire calculation. It does not matter because it's not accounted for on both sides. Now, you have to be careful because sometimes, obviously chemicals are changing. So just because you don't see the exact same chemical again on the other side, that doesn't mean that you can ignore it. If it's changed chemically into new substances, you have to kind of, then you have to keep track of it. So like you'll notice that the ammonium ion is here and that the nitrate ion and its atoms are here. But the hydrogen and the oxygen from the water, they aren't really doing anything, and so we're going to ignore them. So that's pretty tricky. That's not something you're going to encounter very often, but I did want to do one where you kind of saw that just so you know what to do if you did encounter it. So here we go. We have to do a bunch of stuff here. We have to calculate delta H. We have to calculate the change in enthalpy. We have to calculate delta S, the change in entropy. We have to know what temperature that this equation is running at. So we're going to say that the temperature is 25 degrees C. Oh crap, let me erase that. So temperature equals 25 degrees C, which you know by now if you add 293 to that, it's 273 to that, it's 298 Kelvin. 273, right? All right. And then when we're all done with those things, then we can do the delta G. All right. So delta H. This is where those tables come in that I was talking about, because I know that you don't know the heats of formation of these things off the top of your head. So let's grab one of those tables. All right, so let's see here. So this is I want to show you what I meant when I said that the tables won't have every single value you need all the time. So let's look at this table. Scroll down, scroll down, scroll down. Okay, so this one has, let's see, we need three things. We need the ammonium nitrate as a substance, we need the ammonium ion, and we need the nitrate ion. So on this table, you'll notice it has the ammonium ion, it has the nitrate ion, but it does not have the ammonium nitrate, so it doesn't have all of the compounds that we need. So I'm going to look at this one, and on this one we have the ammonium ion, we have the nitrate ion, and then bang, right there we've got ammonium nitrate. So I'm going to go ahead and use this one for my calculations. So if I scroll up to the top here, the first column is my heats of formation, the second column is my entropy. So we're doing heat of formation right now, so what I need to total up all of the heats of formation of the products, which are the two ions. So let's do this. Let's see, NH4 we'll do first. NH4, the ammonium ion, negative 133.26. So come back in here. Oops, negative, now I've already forgotten. Holy cow. Old man syndrome. So negative 133.26. Negative 133.26. Okay, and there's only 1 mole of that, so we don't have to multiply that. If there was more than 1 mole in the equation, we would have to multiply that, of course. And then NO3 is negative 206.85. So negative 206.85. Now I'm going to pull up my calculator real quick, and I'm going to add those together. So negative 206.85 plus 133.26, and remember this, the signs are very important here. So we get negative 340.11. Okay, so negative 340.11. Okay, now let's look back at that table for just a second, because the units here are also kind of important here. So if I scroll up, I find out that on this table, the heats of formation are in kilojoules per mole. That's the unit you want your stuff to be in. You want kilojoules per mole. Okay, and so that's good. We don't have to mess around with the units for that. All right, so now we have one more thing we have to find. We have to find the ammonium nitrate. So let me pull that table back up. Let me pull that table back up. There it goes. So let's see. Right here. Negative 365.6. So negative 365. Well, that's too close to the... Okay, so negative 365.6. And there again, there's just 1 mole of that, so we don't have to multiply it. So now it's the products minus the reactants. So hand it into calculator again, please. Oh, I've already got the products in there, sweet. So minus 365.6, and again, we got to make that negative, or else it's going to mess us up. And what do we get? 25.49. All right, fantastic. So delta H equals 25.49. Oops, my 4 looks like a 9. 49, perfect. Okay, so that is the change in enthalpy. So now let's do the change in entropy, and it's almost exactly the same. Now, one thing I will mention is that you have to be careful. Like if you look at the units on this table, the units are in joules per moles Kelvin, and that's going to mess you up in the end. You have to convert that. So the unit you want is kilojoules per mole. So to go from joules to kilojoules, just anytime you go from the base unit to the kilo of the unit, it's 1,000. It's a factor of 1,000. So basically, we're going to have to divide all of these by 1,000, and I think you'll see why they report them in joules per mole when you do that, because most of these, when you divide them by 1,000, if you look at these numbers, you're going to get decimals, you know, like 0.0 something, point something something. So keep that in mind. If the table that you use has the entropies in joules per mole Kelvin, you do have to convert those into kilojoules. So let's see what that looks like. Let's do the ions first. So we'll do, also notice that there's a state column here. You have to match the state. Make sure you're using the correct state of the substance so that you get the right number. So aqueous ammonium ion, its entropy is 113.4 joules per mole Kelvin. So that's 0.1134 kilojoules per mole Kelvin. So 0.1134. So 0.1134. Oh my gosh, what a horrible 4. I need to get a bigger tablet. Okay, there we go. Really expensive. Okay, so there's only 1 mole of that. If there was more than 1 mole of that, just like with the enthalpies, you would have to multiply by how many moles there are because it is kilojoules, it's joules per mole. So now let's do the nitrate. Aqueous nitrate is 146.4 joules per mole, so that's 0.1464. So 0.1464 kilojoules per mole. All right, and then we've got one more. So let's grab this and we'll do the ammonium nitrate. And this is solid. I didn't look and see. Yeah, it's solid. Okay, good. So that matches, thankfully. And it's 151.1. So that's, again, to convert it, that's 0.1511. All right, and we do this the exact same way. It's the reactant, it's the products minus the reactants. It's the ending state minus the initial state. So let me grab the calculator, clear this bad dog out here. And we've got, what do we have? We've got 0.1464 plus 0.1134. That equals, okay, so I'm just going to write that down. 0.2598. 0.2598. And that's my sum for my products of my entropy. And then it's just 0.2598 minus 0.1511, which is the entropy of my reactant over here. So minus 0.1511. And I get 0.1087. So equals 0.10, was it 87? 87. Bam. Nice. So we found our enthalpy change, which is one term that we need. We found our entropy change by calculating. And we were given our temperature. So we have our temperature. So now we can calculate our Gibbs free energy. So let's just refresh what the formula is. It's the enthalpy change minus the temperature times the entropy change. So for this equation, for this problem, it's the change in free energy, so it's 25.49 minus, and I'm just going to put this in parentheses for clarity here, the temperature, 298 Kelvin, times the entropy change, 0.1087. All right, so not going to do that in my head. Bring my calculator back up, clear it out. 298 times 0.1087. So that's like 32, so 32.39. 32.39. Okay, so now it's just, clear that out again, 25.45 minus 32.39. And we get negative 6.9. Negative 6.9, awesome. Okay, now what does that mean? All right, well, there's a few things here. First, let's talk about endothermic, exothermic. We got a positive delta H. So that means that this is an endothermic reaction, which is kind of fun. Yeah, and yeah, indeed, when you dissolve ammonium nitrate in water, it does get a little cool to the touch. So that's kind of interesting. Second thing is we got a negative delta G. We got a negative change in Gibbs free energy, which is what we're learning how to do. And so what we talked about is, since that's negative, that means it's going to be a spontaneous reaction, which means that once this sucker starts, it's just going to go to completion. And that's why when you throw ammonium nitrate in water, it just dissolves. It goes all the way through and dissolves to completion. You don't have to like keep adding electricity or heat or something like that to it for it to dissolve. So there we go. That's how you do it. There's those steps. You have to calculate your change in enthalpy. You have to calculate your change in entropy. You do that very similarly by summing the products, summing the reactants, and subtracting the reactants from the products. You have to get your temperature into Kelvin if it's given to you in Celsius. 25 Celsius is 298 Kelvin. And then you just use your formula. It's the enthalpy change minus the entropy change times the temperature in Kelvin. And a negative delta G means that the reaction will be spontaneous, and a positive delta G means it will not be spontaneous. So that's how you calculate Gibbs free energy change. Thank you for watching, and as always, if you have any questions, feel free to ask in class.